There's a special trick that can be used with functions as well, called recursion. Recursion is the act of calling the function inside of the function itself. To understand recursion, we need to get a bit technical. Let's look back at the add function, and imagine this call and the print is within main. When the function is called, it's put into something called a call stack. While the call is executing, it exists in this call stack. If the call terminates, either by going through the entire function or when a return keyword is reached, the call is popped from the call stack, and a value is returned. The return value would be null for void functions. So here, the call is popped with the value 5, and the call itself then takes on the value 5, which is then put into the variable sum. But in recursion, function calls can't finish without reaching the recursive call first, meaning additional calls are repeatedly put into the call stack while the original call gets stuck. So here, when the function is first called, it goes to this if statement, but then it hits another call, recur 4 minus 1, or just recur 3. This new call is then pushed into the call stack, and again, the call is ran until another call is hit, so recur 3 minus 1, or recur 2. The only way to exit this loop is for a function to not call itself, which it doesn't in the case that this recursive function is called with a value of 0, as it doesn't fulfill the condition in the if statement. In this case, the print line and the call itself is skipped, so recur 0 finishes, which then allows recur 1 to finish, and the calls in the stack are then popped in order. The total output of this recursive function would be 4, 3, 2, and 1, as this print statement for 4 came first, then for 3, then for 2, then for 1, and since 0 isn't greater than 0, this print line would never execute, giving us this output over here. The important thing to note is that when a call is stuck because of recursion, the call cannot proceed. In this modified recursive function, where the self call is put before the print statement, the print cannot run until the self call is sorted. So again, this call stack fills up, and after the call recur 0 can't call itself, the call stack starts to unwind. But in the call recur 1, only now is the call recur 1 minus 1 sorted, meaning the print statement can only now execute. The same happens for recur 2, recur 3, and recur 4, meaning that the resulting output is therefore 1, 2, 3, and then 4. Let's look at another example of recursion. This recursive function calculates the factorial of an input number. Let's say this function is called with a value of x equals 4. So the call factorial 4 enters the call stack. Since 4 is bigger than 1, it goes into this else branch over here. It says to return x multiplied by the function called with x minus 1. This means that the function call factorial 4 will return or equal the result of 4 multiplied by the function call factorial 3, which also enters the call stack. Now let's focus our attention onto this new call. Since 3 is still bigger than 1, it goes into this else branch again, so factorial 3 then returns 3 multiplied by factorial 2, because 3 minus 1 is 2. And now this new call enters the call stack, and now 2 is still bigger than 1, so it still returns this value over here. So we can say equals to 2 multiplied by factorial 1. And factorial 1 also enters the call stack. But now 1 is equal to 1, so it fulfills this condition right here. So this call will return 1. And because we've returned a value, this call then terminates. And now factorial 1 then takes the value 1. That means that factorial 2 can now terminate because it's returning a numerical value. So this returns 2 times 1, or just 2. So that's popped, and now factorial 2 takes on the value 2. And again, factorial 3 then takes on the value 3 times 2, which is 6. So that's also popped, and now this factorial 3 takes on the value 6. And now finally, our original call, factorial 4, takes on the value 4 times 6, which is 24. So when we run this program, it should theoretically print 24. There we go. Now for recursion to work, two things must be included in the recursive function. First is the presence of a base case. In the factorial example, the base case was that if the parameter is 1, return 1 for the function. Secondly, you must ensure that when you recursively call the function, the new parameter gets closer to the base case each iteration. In the factorial function, every time the function was called, the number got closer and closer to 1. So factorial 4 went to factorial 3, went to factorial 2, and factorial 1, which then got to the base case. These two conditions ensure that the recursion doesn't go on indefinitely. Let's go over another example of when recursion is used in programming. Hopefully, as we go through examples, you'll start to get the gist of when recursion can be used. In this function, we find the value of the nth term in the Fibonacci sequence. The fundamental definition of the Fibonacci sequence is that the first and second terms are 1, which we put as the base case over here. So if the input n is ever 1 or 2, meaning the first or second terms, then simply return 1. Then the third term would be the first term plus the second term, the fourth term is the second term plus the third term, and so on. Let's trace what happens when the function is called with n equals 6. So the call Fibonacci 6, let's just shorten as fib6, is equal to fib4 plus fib5. Now fib4 we can just put in the call stack, fib4 is equal to fib2 plus fib3. And we know that fib2 is just going to equal 1, so we can just put 1 over here. Now fib3 is equal to fib1 plus fib2, and both fib1 and fib2 are equal to 1, so we can just put 1 and 1 here. And because we have 1 plus 1, fib3 will just return 2. So fib3 will be popped, and fib3 takes the value 2. And then fib4 will take the value 1 plus 2, which is 3. So this will also be popped, and fib4 takes the value 3. And now we can focus on fib5. Fib5 is just equal to fib3 plus fib4. And from before, we know that fib3 is just equal to 2, and fib4 is just equal to 3. So fib5 takes the value 5. So we can just remove that, and fib5 will equal to 5. And then our original call, fib6, will just equal 3 plus 5, which is 8. So theoretically, this program should print 8. There we go. When writing recursive algorithms, try doing these two things before writing any code. First, try identifying the base case. This is a fundamental definition for your problem. For example, in factorials, the fundamental definition is that 1 factorial equals 1, and in Fibonacci, it's that the first and second terms are 1. Then, try writing the problem in terms of simpler versions of the problem itself. For example, 4 factorial can be written as 4 times 3 factorial, and 3 factorial can be written as 3 times 2 factorial, and so on. Each iteration is simplified by using the definition of the factorial until we reach 1 factorial, whose fundamental definition is 1. In the Fibonacci sequence, the nth term can be written as a sum of the n minus 1th term and the n minus 2th term, and each of the terms can be written again with that definition until you get to the fundamental definitions that the first and the second terms are 1. Recursion is great for solving certain problems with minimal code usage, but most times, recursion makes solving problems unnecessarily difficult and complex. It also uses up a lot of memory due to the call stack. If the exam questions don't specifically ask you to use recursion, don't be pressured to use it.